guys, are you guys all able to hear me and see the screen?
Yep, can hear you. Can see the slides as well.
All right. All right. Recording's in progress, right? Yep.
Yes.
Yep. See it. Okay, so we can get started, right? So hello everyone. Welcome to Recitation 9. We will be covering CT/CT coding and beam search, things that you will be dealing with for your homework 3 part 2. So before we begin with that, let's introduce the problem statement, the whole idea of sequence modeling and the problems and the challenges that come with it. And then we will go over the strategies that we have in place to overcome those problems. Right? So consider the speech recognition task, right? You have a data set of audio clips and their corresponding transcripts. Now, this audio clip might be a long sequence of feature vectors, and the transcript might just be hello. So there's not a one-to-one correspondence between each feature vector and the words in each letter, or like whatever tokenization strategy you use in the transcript, right? So how do we align the outputs of our model to the label, which is the transcript, right? So this is the whole idea of sequence modeling. And the problem is that there might not be a one-to-one correspondence. There might be, in our case, there's order synchronicity. By that I mean that the order is preserved, so the audio, you're sequentially going from HELLO in the audio as well, but the lengths might not align. And that's the task that you'll be tasked with in homework 3 part 2. So what could be some simple approaches to solving this problem? Well, we could devise a rule like, let's say one character corresponds to 10 inputs. But that's not generalizable, right? Because the way I say hello might not be the way you say hello. So this rule can always be broken. So another alternative would be to hand align each character to its location in the audio. This is kind of like what you did in your homework 1 part 2. So where you had each context-sized feature vector, so each feature vector had its corresponding phoneme label, and then you took a fixed small context-sized feature vector, which you classified into a phoneme. This works well for a modeling standpoint. We know the ground truth for each time step, but doing this is very time-consuming, and it can be prohibitive for large data sets or even mid-sized data sets. So this is where connectionist temporal classification, or CTC, comes in. It gives us a way to get around not knowing the alignment between the input and the output, right? So our main 2 goals are, we need to be able to train a model while dealing with this problem of alignment. And we also need to be able to infer what the output sequence should be from the model's output. All right, so let's look at training. All right, so as we discussed, the inputs and targets are not time aligned, but we need to find accurate mapping from X to Y, right? And as also we discussed, the way I say hello might not be the way you say hello. So X and Y might not necessarily be proportional as well. The ratio of their lengths might not be proportional. So, but as they are order aligned, so we need a way. So we would like to train our model to maximize the probability that it assigns the right answer. So we need to efficiently compute the conditional probability P of y given X. And the function needs to be differentiable so we can train the model. And we need a way to compress the predicted sequence. And uh, and even though and at the same time preserve repeats. We'll see a bit about that soon. By what I mean by that soon. Right. So here's what training would look like. You have a sequence of feature vectors, let's say T feature vectors, and you output a probability distribution at each time step, but your label is zoo, right? So how do you align that long T-length feature vector to just zoo? So how do we transcribe zoo at all these time steps? So that's what CTC will. This is where CTC will help us, right? So we will consider all possible alignments, which will help us, will give us a way to go from probabilities at each time step to a probability of an output sequence. And like for that, we would need to consider all possible forms of valid alignments to a target. Now, models with CTC, like in your homework 3 part 2, you will use an RNN to estimate the per time step probabilities. And now it works well for this task because RNNs have that recurrence, which accounts for the context in the input. But we can use any learning algorithm as long as we produce a distribution over output classes given a fixed slice of the input, right? So let's look at the problem of repetition. So we could solve the whole problem of repetition by a simple rule, right? We could say merge all repeats, but that would lead to some ambiguities. So as you can see here, you have all these words, if we just merge the repeats, would collapse to ZO, right? But we want zoo, ZOO. So we need to merge, we need to be able to compress the output sequence of a model, but also preserve any repeating characters that might occur, right? Also, another reason to do this, another reason is that it doesn't make sense to force every input time step to align to some output, because in speech recognition, for example, you could have stretches of silence in your signal, which with no corresponding output. So the way CTC mitigates this is by introducing a break character, or a blank character as it's sometimes called, which is a new token that is allowed in our set of allowable outputs. And it doesn't correspond to anything, and it's just simply removed. So we produce like alignments that are the same length as the model output, and we will allow any alignment which maps on to the target sequence after we follow our rules, which is merging repeats and removing the blank symbol. And you can see an example here how adding the blank symbol helps. If you add the blank symbol, we drop the blank symbol, and we only merge repeats within the blank symbol boundaries. So now you accurately get zoo. Here's the problem of. All right, so now here's the next problem that comes is there might be many possible candidates of alignment, right? As you can see here, all of these are valid alignments for the word zoo. But if we use time-aligned target, we can compute the differentiable loss. But from all these candidates, which alignment do we choose? So we could use the Viterbi algorithm, which would find the most probable path and use that to calculate the loss. But there's a better option, and which is Using all the additional rules that we have, we can calculate all possible alignments and calculate the average loss over all of them. And by the additional rules, we have that x and y are monotonic. So once you advance to the next input, you can keep the same output, or you may advance to the next output, right? So let's say A is followed by a B in the target. So when you're at A, you could either go to a blank symbol, or B, right? And the alignment of x to 1 is many to 1. There might be many input elements that align to a single output element. And length of x has to be greater than the length of y. All right, so the entire task breaks down to you're given the break character or the blank character, the order alignment, and some additional rules. We have to find all the possible alignments, their probabilities, and then calculate a differentiable loss. So let's go through the training process.
I think there's a question on Zoom.
Oh, sorry. I can't access the Zoom. Alex, could you tell me the question on Zoom?
Sorry, there's a question. Let me see. So it's what is considered when introducing blanks in between the output?
Sorry, I couldn't hear that. Could you say that again? Did you hear that?
What is considered when introducing blanks in between the output?
What is considered when introducing blanks in between the output? I'm not sure I understand that question. Could you clarify, whoever asked? You're just adding the blank to our set of, let's say you have your, oh, what is the strategy used? Oh, okay, so you just, let's say you have your vocabulary, right? You just add a blank symbol to your vocabulary so that the model can generate a blank and learn to generate a blank. And then we use that blank symbol for our heuristics here, which is to like merge all repeats and collapse. Merge all repeats and then preserve the repeats based on the blank character, and yeah, collapse the input to the output. And so we introduce the blank character so the model can learn to generate the blank character. Does that answer your question? Okay, cool. You can go.
Okay, let's take care of the training part by CTC loss. So just to make some clarifications, the model will generate possibilities for all the available vocabularies at each time step. And our goal is to transcribe Zoo at these time steps. That's our target. Yeah. And by that, we mean, so for example, we have a list of vocabularies from A to Z in this case, and we just want to like calculate the CTC loss by that. And in this case, we just limit those characters in the target with breaks inserted. And it might be easier to use these visualizations to discuss the same way we used in the lectures. And this lists out all the possible paths from the start to the end, given a fixed length of the input. And we should know that not all these paths are viables, and there are usually two cases. It either breaks the additional rules we mentioned before. In most cases, it breaks the monoticities of the path, or it just cannot reach to the end of the sentence given the time steps remaining. And we will see some examples later. Yeah, here. So at least it is good to start start considering these questions from the start and the end, from the outer edges, at least it is easier for me. So can anyone tell me what is the starting path and the ending path, given that this input has to like start with Z or break and end with O or break? Okay, just to save time, so I'm just gonna tell you. So it has to like starts as this, starts with Z or break or end with O or breaks. And if we move one step further, it's gonna be a little bit more complicated. And we also need to, this also lists all the possible paths, but not all of them are viable. And we should know that there are some like horizontal paths, for example, from break to break, and there's a downward path from breaks to breaks too. And we can spend some time considering what's the difference between two and which one is viable while the other one is not. And we can see that the downward path it is not viable because it just skipped the Z, the first Z, and there's no chance to get another Z in the following time step. So that is not a viable path. But on the other hand, the horizontal path from the break to break it is viable because you still got a chance to reach Z in the following time step. So this is the all the viable paths for the first two layers and the last two. Yeah, and let's move one layer forward. Yeah, and we can consider in this path. This path won't work because it will skip the first O. As I mentioned before, the path is not viable because it either breaks the monoticity or it just cannot reach the end of the sentence by the limiting time step. And we will see another examples about that. So yeah, in this case, if you consider this edge in dotted line, this path is not viable too because you won't be able to get to the final character based on the segmentation length. So you can see that if you need at least a break between two O's based on the repetition rules Peru has mentioned before. So for the remaining time length, there's no ways to reach the end of the sentence.
There's a question.
Oh yeah, what is it?
Disappeared.
Yeah, Alex, can you do me a favor? Tell me what is the question?
So it's basically asking what is monotonicity in this case, which I believe is just going left or down.
Okay, so I will go back to the slides talking about the monoticity.
It's just going left or right.
Yeah. So basically, definition of monoticity is like alignments between x and y are monoticity. Once you advance to the next input, you may only keep the output same, advance to the next output. It basically means it cannot go back. You have to stay at the same time step or move to the next. And I think it is important to, yeah, I know it can be confusing, but I think it is important to know how these graphs work. So this graph is more like visualizations that illustrate how monoticities work. So it lists out all the possible paths in a readable ways. So you can notice that there's never an upward path from the previous layer to the next. That is because you can show the monoticity clear. So if you want to in some cases like this, if it moves if it is skipped the first Z, it is not viable. So you can see it very clearly from this graph. But if you use another form of visualization, so for example, if you say, okay, I only got break Z and O, so I'm only gonna draw like a graph that containing 3 rows. That's gonna be a mess, and there's no way you can see how monoticity works in that way. So this graph is more like a visualization, and it is not like, it is just try to explain how this path works, and it clearly show why some paths are not viable. Does that answer your question? And if not, we can discuss it like later. Okay, nice. Yeah, I know the graph can be confusing. It definitely confused me when I like learned this concept, but yeah. But after that, I realized it's just a way of visualization. Yeah, and this is a good example of what I've just said. So the body line, so these are already all the viable paths, and the body line are like viable skips, if you said. So there are many skips in the graph before, but most of them are not viable because it either like skips some important, because for example, this path skips O.
No, it's Alex thing.
What did he say? What did he say?
You're correct. Answer your question.
Okay, okay. Nice. So this is a not viable skip example. So you cannot just skip like that because it skips the O and there's no chance to, because you need two O. Although there's another O in the following time step, but you need two. So this is not viable. So in summary, if you want to consider if a path is viable, you either consider if it follows the monoticity or it can reach the end of the input given the time steps. Okay, so now I have already got all the viable paths, and now I'm ready to calculate the posterior probability given the forward-backward algorithm. I think Professor has covered it in depth in the lectures. So if you don't understand it, you can just go back to check the lecture recording or the slides. But basically, once you have all the viable paths, you are able to calculate the posterior probability of a certain character appearing at a certain time step by like calculating the probability in two ways. Yeah, and after that, we have all the probabilities we needed, and the functions is also differentiable, so we are ready to like calculate the expected loss. Yeah, and now we are ready to train because we have already solved the like time alignment problem, and we also solved the repetition problems, and we got a differentiable loss function. So yeah, and this is just a summary of everything you need to do for this homework. So first of all, you're gonna define a model. Basically, you can define any model you want to use, but in this homework, you are likely to work with a bidirectional LSTM. And then you just initialize the network to output targets, and you don't forget to add the break characters, as I mentioned. And you just pass the training instance through the network to obtain probability distributions over the labels. And then you construct the table of viable alignments. And then you use the forward-backward algorithms, compute the expected loss, and then you can just go for another run and train and train and train. Yeah, this is just visualizations of everything that you need to do. I think Pro has also included these visualizations too, so yeah. And now, Alex, do you want to take over with you? Okay. Yeah.
All right. So, well, the key thing to remember is that CTC gives us a way to consider all possible alignments to a target so that we can compute a differentiable loss by averaging over all of these alignments and train a model, right? So we've trained a model. So there's a lot of details in between these steps, which you can refer to the slides. But we have a mechanism for training the model. So what do we do? Now, how do we infer from it? Because that's the next key step, right? So what are the challenges So we would like to infer an output sequence given our model will output probability distribution over our entire character set or symbol set or output classes, whatever we have, whatever you're using at each time step. Now, how do we infer the output sequence, right? What is different at inference? Well, you don't have a target, right? So you don't know what you're aligning to. During training, we have a target, so we could find all viable alignments and compute a loss for it. But there is no target. And so there are no sequence rules that we can follow, right? So what do we do? So how do we decode the output that the model will give? All the different, at each time step, it will output a probability distribution. And how do we, how do we find what would be the valid output sequence, right? So there are several algorithms that have been proposed for this. Yeah, the trees get large. So what are options? Exhaustive search is prohibitively expensive. We can't consider all different combinations of alignment. So the two alternatives that we will go through is greedy search and beam search. So greedy search is pretty straightforward. It's a simple heuristic. So you're getting, at each time step, you're getting this probability distribution. You just take the most likely one at each time step. And then you follow the same rules. You collapse the repeats, remove the blank tokens, and that's your output sequence, right? So for many applications, this heuristic works well, especially when you have, like, most of your probability mass is allocated to a single alignment. But there are some problems. There can be some problems with this alignment, right? So you're only considering you're only considering the most probable output at each time step, but that might not be the most probable path, right? So the main problem is that it doesn't. So we trained our model with CTC, but it doesn't take into account the fact that a single output can have many possible alignments. So an example of this would be, let's say we have the alignments AA blank and AAA. Now, individually, they might have a lower probability than, say, BBB, right? But AA blank and AAA, according to our CTC rules, collapse to the same output A. And BBB would collapse to B, right? But since with greedy search, we are only considering the most probable alignment, our model would output B, when A would have been a better output because the sum of all possible alignments of A that give the output A has a higher probability. So to fix this, we need an algorithm that needs to account for the fact that AAA and AA blank, they collapse to the same output. So let's walk through a greedy search example. We have time step T0, T1, T2, T3. So at T0, the highest probability, A has the highest probability. So we give A, B, and then A, B, and then our decoded string is AB, AB, and we just multiply all the probabilities to get the total probability, right? But now we'll explore a better algorithm that attempts to consider some of the CTC rules, which is beam search. Go ahead, Alex.
Okay, do I share my screen?
You said you want to share your screen?
Yeah, let me try that. I think it should allow me to move a bit faster.
Okay,
cool. I hope you guys can see it. Puru, can you let me know if it's visible?
There's some blank, like dark patches on my end.
Oh, okay. Maybe we just let you share. Sorry for that.
Okay.
Or is it the meeting panel? Okay.
Yeah, I think it's the meeting panels that are popping up. You can hide them.
Okay. Uh, okay, sorry. Can you guys just share instead? Sorry for that.
Okay. No worries, no worries.
Okay, great, thanks. So we've seen that the goal of inference is to find the most probable sequence, which beam search can't always do, and we'll show an example to just to highlight how it can get trapped in a local minimum. So please go to the next slide.
Sorry, Alex. I am a little stuck trying to find the control. Oh yeah, okay, cool.
Okay, cool. So let's assume that the vocabulary is just, 4 words. So it's the, cat, sat, and high. And for some reason, we do know the target sequence, which you wouldn't know at inference time. But because the model was trained on maybe some conversational, a conversational corpus, the word high tends to be the most likely at the start of a sequence. And so you end up, if you use grid search, you just select the most probable word at that time. So here you end up with selecting high, but then the target sequence is the cat sat. And so with grid search, for this example at least, it's not possible to decode the correct sequence, correct in this case being the most probable sequence. Next slide. So how do we fix this? One way is exhaustive search, which means that at each step, you're considering everything, right? You're considering the entire vocabulary at each time step. You do not drop any parts as you decode. But as it was said, this gets really expensive really quickly because if your vocab is bigger than this, then you'll be doing a lot of computations at each time step. So beam search is a trade-off in between the two. So next slide. Yeah, so in this case, for example, we need a beam width that's at least 2. So we're taking the top 2 at each time step. If we take the top 2 here, we can consider both high and the, and so we won't, be shut off from the most probable sequence. Whereas in beam search, we would not be able to find it. Next slide. Yeah, so this is basically the spectrum. You can think of greedy search as a special case of beam search. So that's K is 1. So you can think of greedy search as a special case. Sorry, that's when K is 1. It's fast, but you can get trapped in this local optima. Exhaustive search is also another special case where K is equal to the vocab side. This is expensive, but you'll find the most probable path. Beam width is something in between. It allows us to trade off speed or costs for performance. And we'll look at an example of beam search here. Next slide. Yep. So here we have the same table, same set of symbols. That's blank A, B, and C. At time step 0, we have the probabilities for each time step. So the probabilities are the columns. Next slide. So at time step 0, this is basically like the start of the decoding, right? So the scores for each symbol is basically how likely that symbol is given the start. Here we can see that for this example, we'll use a beam width of 3. That means that at each time step, we're considering the 3 most likely paths. So in this case, if you look at the top 3 scores, that's A is the highest, followed by C and then B. So these are the 3 that we'll take as we go to the next step. Next slide. Yeah, so that's basically it. So our new path is ABC. Now we'll go to the next time step, that's T is 1. So here we now consider that, if you start with A, you can also be followed by any other of the symbols in the symbol set. So you basically build a symmetry, a hypothesis symmetry. So starting with A, you can end up with a blank. Starting with B, you can end up with a blank, and so on. So you end up with this possible path. In this case, that's, I believe, 12. And you calculate the score of that path. So the score of A blank is basically the probability of A at time step 0 times the probability of blank at time step 1. And then you compute these scores, and since our beam width is 3, you look for the 3 highest at this point. Next slide. Yeah, so the 3 highest end up being A blank, AB, and AC. And so here we've updated, on the bottom right, we've updated our new set, our new path. So we'll go now to this second time step, T is 2. So now we'll consider all of the best paths and then extend them with each of the possible symbols, right? So we had A blank as one of the best paths from the previous time step, and so we'll extend it with each of the symbols. So A blank, blank, A blank, something else, and so on. And then similar thing, compute the scores along that path, and then take the top 3. This is the point where I think, you don't need to consider some of the previous rules that we set. So for example, if you have A blank A, you have the same symbol on both sides of the blank. So it tells you that that's a valid repetition. And so you do not, you don't compress them into a single A. So we see A blank A, that's the 4th row. It's effectively AA, right? A blank B is AB. But here below A blank B, we see ABB, and we don't have a blank between the two Bs. So that's effectively telling us that there was a repetition there. And so, it's repeated in the, you shouldn't keep that repetition as you continue decoding, right? So if it was A, B blank B, then that would be ABB. But without the blank, it means that the two Bs are basically 1. So yeah, let's go to the next time step. Yeah, so again, we take the top 3, and this is what we have at T is 3. T is 3 is our last time step. So again, we're applying the same rules. If you see a blank between, I don't think we have such an example here, but then, if you do not see a blank like ACAA, that's, I believe, the 6th row in this table. So there's no blank between the two A's, and so, yeah, it's ACA. Again, take the top 3. If you have any blanks at the end of the sequence, you should remove them. So we end up with our new 3 best paths by maintaining a beam width of 3 throughout the decoding process. Next slide. Yeah, so this is the algorithm. So I think as far as completing the homework 3P1, we provide there's one method discussed in, there's pseudocode from the lecture slides that I think is good, but this is slightly more efficient. I think it's good to try both. If you have time, do try both. I think there's a lot to learn from each implementation. But yeah, again, do consider that there are 3 possibilities as you're extending a path with a new symbol. One is that the symbol is the same as the last symbol on the path. 2 is that the last symbol of the path is blank. And lastly, is the last symbol of the path is different from this new symbol, and it's not a blank. So we'll apply the same rules that we've been applying all through. And so I think it's good to refer to this as you do the 3P1, should be helpful. I think it's best to try both approaches. Next slide, please. Yeah, so this is effectively illustrating the process that we're just describing. So at each time step, you build, a hypothesis symmetry from the paths that you're considering. So like at the first time step, we were considering A, B, and C. And so we'll build three symmetries from each of these paths. And then we'll, do the process that we found, which is computing the scores, taking the top three, and then again, build another symmetry from those top three. I hope this helps to kind of illustrate it. So we also have some extra notes that I think are good to consider. So beam search or even exhaustive search is not an alternative to training a model to output good probabilities. So if you do beam search over, a bad model, it wouldn't be better than a good model with greedy search. So, the primary thing is this is supposed to help a good model get better, not a bad model get good. Also because of the additional time complexity, considering more than one path, people tend to use a smaller beam width for validation and then use a larger beam width for inference. So you're keeping your time, you're reducing your training time by not having a very large beam width while validating. And some other extra notes on the next slide. I think something to think about is, can we expect monotonic performance as we increase K? So monotonic performance here means that using the test metric for the task. For example, if it's speech recognition, maybe it's a quad error rate or Levenstein distance, maybe. Do we expect performance that either improves or stays the same as we increase K? To me, this is, when I first heard about beam search, I think I assumed that this is true. But we've attached some readings here that, if you want to look into it a bit more, people have found that this is, it's not always the case. But it's good to consider why. And I think each of the papers are pretty interesting, and they do explain this in interesting way. So yeah, that's it for my side on beam search. I can hand it over back to Uru and Andy.
All right. I think that's it for the entire recitation, right?
Yep.
Yep.
All right, guys. Anybody has any questions, we'll take them. If not, best of luck for homework 3 part 2. You'll see the slides and the video on our website as usual. Any questions?
Yes. Can you share some hints about how we're going to handle the data loading for this assignment, different from what we did for assignment 1?
So we'll have a homework 3 part 2 bootcamp tomorrow that will go through over all the homework 3 part 2 specific implementation details, right? So
All right, thank
please
you.
attend that.
I think there's another one on Zoom.
Sorry, is there a Zoom question, Alex?
The question is, how do we ensure that we eliminate the blanks during inference? So, we'll use the same rules as we did. So that's, if you see a blank between, so the blanks are not actually part of what you expect to see as the final output, right? So a blank between two of the same symbol will tell you that you should keep those symbols. So like if it's A blank A, it means take out the blank and then keep both A's. But if it's AA without a blank in between, it means keep only one of those A's. So at the end, we won't have blanks during inference. If you have a blank at the end of your path, at the end of the sequence, you'll remove it at the end. But then you shouldn't have, in the final output, you don't expect to have blanks, because the blank it's a special symbol. It's not, it's not part of the speech. Yeah, I hope that's clear. Okay.
All right. Yeah, so also, were you sharing something, Alex?
No.
No, no, all right. All right, so make sure we have a homework 3, a boot camp for the entire homework 3 tomorrow, I think. Is that correct, Alex, Andy?
Yes.
Yeah, right, so make sure you attend that. That will answer a lot of the homework 3 specific questions you might have. All right, guys. Well, thank you guys for listening, and best of luck on the assignment.
Oh, I think I want to ask, when is the slide available?
Oh, when's the slide? Well, who's okay? Yeah, we'll try to get them up as soon as possible. Like definitely by like the end of today for sure. Maybe earlier. We'll make a post about it too. Sure.